Most of the time, when we talk about geophysics, we mean the seismic method. Or there are other geophysical methods, and in later modules we shall talk about those. But in petroleum exploration, 95% of expenditures on geophysics are in fact for seismic work and for seismic reflection work. Reflection, we all know the principle. We make a bang and we listen for the echoes. We make a bang and we listen for the echoes. With these geophones, little microphones, if you like, earth microphones, to detect the reflected bang. Let's see what happens.
Here at the Grand Canyon, we find a vast thickness of the geologic column exposed. The Colorado River has given us a section through the rocks. Basically, we are seeing through the trees 4 major geological contacts, here and here, and here and here.
Okay, now let's make a bang at the surface here. We'll need a big bang, so we'll use a charge of explosive. To make sure we don't blow ourselves up, we'll drill a shot hole in the surface rocks and put the explosive down there. Shot point 1. Ready? Contact. Shoot. The earth trembles. The bang spreads out. Again. Propagating through the rocks, each rock layer trembling a little as the bang hits it. Again. This is just about the speed it happens, just about the velocity with which the bang spreads out in the earth. Let's see it in slow motion.
We shall call the bang the seismic source. We shall call the spreading tremble the seismic wave. And we shall find that the seismic wave shares many of the properties of other waves we know very well, including the property of being reflected. Again.
And so it is with seismic waves in the earth. The wave goes down and is reflected, or in slow motion. Again, watch for the echo as it comes to the surface. If we had one of our little geophones right there, we could detect the echo. Again.
Okay, now let's go back to the pond for a moment and see if we can arrange the reflector to demonstrate partial reflection. Yes, there it is, partial reflection. Some comes back, some goes on. Some is reflected, some is transmitted.
And so it is with geologic contacts in the earth. When our spreading wave meets a reflecting interface, part is reflected and part is transmitted. Again, still in slow motion. Just as the wave meeting the first interface is partly reflected and partly transmitted, so it is with the second, and with the third, and with the fourth. Or in real time, and in slow motion again.
See those 4 reflections detected at our geophone? Blue for the shallowest reflector, yellow for the second, orange for the third, red for the deepest.
So, we make a bang. The earth trembles, and the tremble travels out in all directions as a seismic wave, reflected in part, and transmitted in part at each geological interface. But often, for simplicity, we think of it less in terms of waves than in terms of rays. The downgoing and reflected ray for the first reflector, and the second, and the third, and the fourth. And all together. And in real time.
So we have the two views of what happens in the Earth, the wave view and the ray view. The wave view and the ray view.
Remember, the wave view is what actually happens in the Earth. The ray view is very useful for calculations.
So the good geophysicist uses rays, but thinks in terms of waves. Mark my words, it's important. Think in terms of waves, and we'll drill fewer dry holes.
Obviously, we need to be rather nimble to catch those echoes. For reflectors this deep, the whole thing is over in about half a second. So we'd better capture the output from the geophone by recording it on tape. Then we can take away the tape and examine it at our leisure.
Here's one thing we might do. Let's play back the signal from the tape as a wiggly trace. Let's look at what the geophone heard. There it is. That's what came out of the geophone. The vibration of the ground as a function of time. Again.
Now, my goodness, what does all that mean?
Let's take the events one at a time. First, this marks the instant when we made the bang. We call it the time break. It's the effective time origin of the recording, the zero time point.
Next, the first arrival through the Earth. See where that comes from? Yes, you're right. The bang makes the Earth tremble, and the tremble travels more or less horizontally to the geophone as the first arrival, or the first break. Now, the first arrival tells us absolutely nothing about reflections, and for present purposes we don't want it. So we mute it, remove it, cut it out.
That leaves us the four reflections, the four reflected trembles as a function of reflection time. The reflections get progressively weaker, of course, as they have further to go. Supposing we could remove that effect, that loss of strength with distance traveled, so that this would become this. All reflections now have equal strength.
All right, now let's cut out that trace and stick it here. One look at that and you've already guessed what we're going to do next. Yes, move the geophone to here. Make a new bang here at shot point 2 and play out the geophone signal in the same way. Do it again at shot point 3. And again at shot point 4, and so on. You can see what we're doing, building up a seismic section as a representation of the underlying geologic section.
Let's look more closely at this seismic section. Its horizontal scale represents horizontal distance along a line, just like a geologic section, shot point 1, 2, 3, and so on. Its vertical scale is in seconds of reflection time, down into the Earth and back.
Although the seismic section is composed of vertical traces, we can convey the impression of horizontal lines, marking the rock contacts, by the simple trick of blacking in one side of the wiggles. So here is the tremble reflected back from the first rock contact here from the second, and so on.
We are representing the geologic section by the seismic section.
And that, in principle, is seismics. The fieldwork yielding the magnetic tape, the processing yielding the seismic section, and the interpretation seeking to derive the geologic section from the seismic section.
Again, the field work, normally done by a contractor, obviously in the field.
The processing, sometimes done by a contractor and sometimes by the oil company in a processing center.
And the interpretation, almost always done by an oil company interpreter in the company offices.
Let's take a look at the field work. It starts with a map, perhaps a topo map, showing the lines, showing the grid of lines to be shot.
Remembering our last tape on the exploration task, we know why there has to be a grid of lines, to get a grid of sections, and so a contour map. It's our way of seeing the structure in the solid, so to speak.
Perhaps a line is more or less along a country road, which would be convenient. More likely, it has to go across fields, or through the swamp, or across desert, or through the bush. In any case, it's very important that we put each line on the ground exactly where it's supposed to be from the map. That is a job for the surveyor.
The surveyor also must mark off along the line, with numbered stakes or little flags, the positions of all the shot points. And he must prepare a shot point location map, showing these positions accurately. Heaven forbid that we discover a structure, get ready to drill it, and then find we're not sure where it is.
Then we must drill a hole at each shot point to take the explosive. So the driller sets up on the little flag and drills a hole wide enough to take your fist and as deep as a tree.
If possible, we like the hole to go right down into good solid earth, below the loose weathered soil, and preferably well below the water table.
Then we take a stick of explosive, perhaps 1 kilo, perhaps 10. Add an electric detonator, which we always call a cap, and load it, rather carefully, down the hole. We connect the cap wires to the blaster, and we're ready to make the Big Bang.
Meanwhile, we also plant the geophone. In the very simplest sense, we need only one. But normally, we use a group.
There are several reasons for this. Let's just mention two. The first is that a single geophone hears not only the trembling of the earth due to the reflected bangs, our desired reflection signal, but also the swishes and swipes of the leaves blowing in the wind, an undesired noise. If we use several or many geophones all connected together, the signal coming up from below is the same for all of them, while the wind noise is different from one geophone to another, particularly if we space the geophones out a bit. The group improves the signal relative to the noise.
Improves what we call the signal-to-noise ratio.
Right. A second reason we use several geophones in a group is just to reduce the effect of one geophone plant, which is highly anomalous.
Like this anthill.
So then we connect the geophone group to the recording truck. Check that the recording instruments are all fired up. Ready? Contact. Shoot.
Meanwhile, down in the earth, the seismic bang is being reflected. The reflections are detected by the geophone and recorded on tape. Safely captured. The observer writes down what file on tape goes with what shot point on the map,
Repeats the whole process at shot point after shot point right along the line.
Here you go.
Thank you. And sends the tape to the processing center. Well, in a processing center, unlike the field, it really is difficult to see what's going on.
First, the data are prepared for processing using the surveyor's map and the observer's report, and the experts decide what processes should be applied. Then the field tapes are sent to the computer, which gobbles them up and thinks a bit, and spits out a new tape. The resulting displays go back to real people who decide the next processes and variables to be applied, and so on. The final tape goes to the machine which plots the seismic section.
So although there isn't much to see, a great deal is going on. And the object of all this is to make the seismic section as close as possible to the geologic section, to remove the unwanted artifacts of the seismic method.
we have already mentioned two of them. The first break, because it's not reflected, has no function, no geological meaning on the seismic section. So, we mute it out. In the same way, the fact that reflections get weaker merely because they get deeper has no geological significance, so we remove it.
Next, we remember from our last session together that we must refer a geologic section not to the surface, which has hills and valleys, but to a datum plane, such as sea level. So we must remove the effect of the seismic travel in the Earth between the surface and the datum, correct all reflection times to what they would have been if both the shot and the geophone had been at the datum level.
Next, we have to worry again about noise. If we're hoping for reflections from very deep in the Earth, they're going to be very weak, and we have to hear them against a background of noise from the wind, or of noise generated by the shot, or of noise from factories or tractors or traffic. So we have a number of programs which we can apply to minimize the effect of the noise.
Next, we note that whereas the contact between two rocks may be sharp, the reflection which represents that contact on the seismic section is not sharp. What we would like to have is sharp reflections, so that by blacking in one side as before, a sharp contact on the geologic section would be represented by a single sharp alignment on the seismic section. The reason we don't have this sharpness is that when we make a bang, even a very sharp bang, the Earth trembles. The form of the reflections represents that tremble. Another of our tasks in the processing, then, is to try to sharpen this tremble, to try to convert it into a single alignment representative of a sharp geologic contact.
And let's mention just one more task, the problem of dipping reflectors, like this one. Remember what we have said so far. The reflections come from below where we are on the surface, and that's where we plot them on our section. But if a reflector dips, the reflection does not come from below us. It comes from a point up dip.
Memento, why that is?
No dip, dip. No dip, dip.
See, of course, okay.
So if we plot this dipping reflection vertically below us, as we normally do, the seismic section does not show the dipping reflector in its correct place. Instead of being here, it is plotted here. Instead of here, we plot it here. So as a late stage of the processing, we often apply a program. We call it a migration program, to move the dipping reflections up dip, where they came from.
So having applied some or all of these processes and plotted the results, we send the resultant seismic section to the interpreter.
Now, what is it that the interpreter looks for? First, the horizontal scale of the section. Second, the datum, which in this case is sea level. And third, the vertical scale of the section in seconds of reflection time down into the earth and back. In this case, some 3 seconds of good reflections, many of them continuous right across the section. And there's a structure there. Do you see it?
Well, you mean...
Okay, so we have to give away one of the tricks of the trade. First, we look at the section face on, like this, to get the scales and the general appearance, just like that. But then we turn it sideways, and we squint along the reflections. There, do you see? And now, if I swivel slightly.
Sure, easy. Up and over. Good closure.
Right. So, that's the trick of the trade. Turn it sideways, squint along the reflections, swivel to pick up the dips, and then say, Remember not to say anything definite, lest you get caught out. Make any noise you like, but nothing definite. Here, let's do it again. Now, there's a nice reflection. Continuous, shallow, no dip. Below that, 3 beauties. There's 1, and 2, and 3. Below that again, greater closure. You see this? Greater closure. And deeper still, we have this one. Now, let's pick this reflection. A good interpreter keeps his marking very light in order not to obscure the subtleties. But for the purposes of the video, we will mark this with a good, bold color. Up and over. We are picking the reflection. There. Now let's take a look at that.
Okay, I see what to do next.
You do?
Yep, we've done it before.
Bravo. You remembered. Mark the datum. Measure how far the pick is below datum, here and here and here and so on. Transfer the values to the map. Add the values on the other seismic lines and contour the values.
I could do that.
Go ahead.
Squint low, take the yellow pencil, mark my pick. There, that looks good. Time the reflection below datum. Post the values on the shot point location map and contour them. Hey, Pepe, look at this. Squint low, pick the reflection, time it, post the values, and contour. It's easy. Then look for a spill point, put in the oil-water contact, and that's it. Pepe, I can do it. I can find oil.
George Fuzzy would smile, wouldn't he? He remembers that feeling. So do many of us. The scene changes. In every major petroleum city, there is a tall building at whose tallest top sits the Petroleum Club. But today, we look beyond that to the great Petroleum Club in the sky.
Where the entry requirements are very different. Number 1, no problem. And be prepared to stand up in full session of the club and say why it was dry.
So that everyone learns, but no bragging about successes. You get absolution only by being humble about dry holes.
Ah, so despite the dry holes, this is a club for successful oil finders. Let's listen in as a new applicant faces the club.
Ladies and gentlemen, the dry hole I recall most clearly was on this most classical of structures, southern North Sea, you know.
That looks familiar.
Suddenly, I have a sinking feeling.
Actually, it really was the most super prospect. Sheer delight to pick. You can see where I picked the top reservoir. And sheer delight to contour. Everything absolutely top hole. The reservoir sand was well established in the area, and thick, there it is, and well sealed above. Sort of prospect one dreams about, what? What indeed? Salt, ladies and gentlemen, salt. That's what went wrong. Salt, you can see it forming a pillow here. Actually, the very same pillow which uplifted that beautiful structure above. And you notice that although it thins over there to the right, it still presents a uniform impermeable barrier between the rocks below and the rocks above. They are indeed carboniferous right at the bottom of the section. Have to confess I did. No good saying I didn't, what? But that beautiful structure, by Jove, the most elegant structure I ever saw. How could I resist drilling that? Well, first and foremost, of course, that structure alone is not enough. And second, that in a situation like this, with an impermeable barrier between source rocks and reservoir rocks, one must look for a migration path through the barrier. Well, yes, sometimes, if you're lucky. Arco and Phillips were lucky like that, in the Hewitt field. Same situation, basically. Source rocks down here, a salt layer in here, the reservoir sandstone here. And the timing and throw of the faults was just right to let lots of gas through. Doesn't always happen, though. You see, here at Hewitt, the salt layer was thin. When the salt is thick, as it was in my structure, then the salt can absorb the faults without letting much gas through. Here's one I should show you. Not long after my big salt gaff, I had to make a decision on this prospect. Another beautiful structure at reservoir level over a salt pillow. Source rocks below, and a big fault, but totally absorbed in the salt. So I had to hope that all this disturbance here, where the salt had broken through and initiated a salt dome, would have opened a migration path for enough time to get oodles of gas through. Well, some got through, but not oodles. It would have been a jolly good gas field on land, but at sea, alas, not enough to be commercial. Had to drill it, though. Very fact the gas was there proved I could have missed a field if I didn't drill. Much safer than a fault in this situation would be a local but total squeezing out of the salt. More like this. That would make a pippin of a prospect, what? Oh, I say, thanks awfully.
Meine Damen und Herren, ladies and gentlemen, the dry holes I have. One, it is like this, just like this, with the salt. But the reservoir, it is here, under the salt. The salt is the seal, yes? And good structure I have, good structure to reservoir. So I drill. It is a dry hole. Why is it a dry hole? There is no structure. But the structure, you can see it, no? The structure, it is an illusion. It is not there. And I am a Dummkopf. Always we have to remember the seismics, the vertical scale it is in, the time,
not in the depths. So, if in some rocks the seismic wave it travels fast and the other rocks it travels slow, yes, we have some problem. Here, I show. Datum, yes? Here is topsalt. And basalt, which is top reservoir. I draw in the depths now, in meters, yes? And in the depths, in meters, there's no structure on the reservoir. The reservoir, it is flat. But in the time, the reflection time, what is it in the time? In the salt, the wave travels fast. In the rocks, on the flanks, it travels less fast. So the reflection time here, where the salt it is not, that is long, yes? But the reflection time here, through much salt, the fast salt, that is less, no? So if I draw it now in the time, not in meters, but in seconds already, what happens? The reflection from the top reservoir, it is early coming. Very early coming where the salt is thick. Just a little early coming where the salt is thin. So we have structure, but it is not structure. It is an illusion of structure. And I have a dry hole. Number one, remember please, the vertical scale of a seismic section, it is the time, not the depth. Number two, where we have a fast layer, like the salt, yes, or a slow layer either, eh? And the thickness of the layer, it changes, we have false structure under dry hole. Yeah, slow layer either. For example, water. The sea, yes? Ein jellyfish, eh? Deep water to the right is, and water slow. So reflection time, it is long to the right. Two faults down to the right, yes? No doubt about that. And the reservoir, also it dips to the right, on this seismic section. But is it in the earth to the right dipping? That is the question. Hamlet, yes, that is the question. For these problems, for all of these problems, we have to know how fast travels a seismic wave in the layer. The salt, yes? Or the water, or the other rocks. We must know the velocities, the velocities. Then we can work out the real depths in meters, eh? And the real dips, which way they are going. Danke, sehr gut. Well, gee, guess it's me. It's funny, but the only dry hole I drilled was just like that there. Stair-step fault and down to the east. Yeah, just the one. Went into administration after that. Figured one's enough. Just like that. Drilled the fault trap, plumb smackety-dab. Only it weren't there. Nary a nothing. Good reservoir, thick and porous, but wet. Just a small show of oil at the top. Corrections? Gee, so I should have drilled way over here. And then I would have found... Oh, that means... that means I missed a field. Yeah, but you can't do that to me. I'm a manager. Oh, hell.
Hi, call me Jill. Dry holes? I've had my share, I guess. For instance, this one, up in the North Country, there's a good-looking structure for you. Go ahead, take a look. Yep, there may be a small fault there, but the way I figured it, we'd have to rely on the dip for closure. Well, believe it or not, on that structure, and in big-time gas country, too, on that structure, I drilled the driest dry hole I ever did see. Not even a puff of gas. I'll tell you, I was surprised. The reason for it was this valley. Oh, sure, I knew the valley was there. I saw it on the topo maps. But that was reasonable enough. In this area, the surface sort of halfway follows the subsurface anyway. Leastways the major features. And I knew there was a risk in correcting everything to datum. So I checked these processing guys real careful. checked the elevations of the surface above datum, so many feet, checked that they'd used a reasonable velocity for these old rocks, about 12,000 feet per second it was, I remember, checked the arithmetic, like if the elevation was 1,200 feet and the velocity was 12,000, that was 1/10 of a second on the way down and another 1/10 on the way back. So to bring the reflection time to datum, they had to subtract 2/10 of a second, right? And here in the valley, only half as high, subtract only half as much, right? Well, I checked all that. I even checked what happened if that velocity was not right on the nose. And it was all right. The structure was still there. Of course, it changed the closure of the structure, but for all reasonable velocities, the structure was still there. Fill. Fill in the valley. I should have guessed, really. I knew that it had been a glacial valley. Could see it from the topo map. And I knew there was a deep glacial lake upstream of it, to the north. So I should have expected lots of loose fill in the valley. Low velocity. Low velocity in the loose fill. Half even. So now, if we do the arithmetic, we have to take 2/10 of a second off the reflection times instead of 1/10, which would raise the reflections under the valley by 1/10 of a second. And so, boom, destroy the closure. All we would have left is the regional dip. And, of course, no gas, not one puff, not one piddlin' puff. Well, like I say, I should have paid more attention to the near surface, the known glacial history and all that. See, even a few phone calls could have told me. There are towns in that valley, and I could have called a water company, asked how deep were their water wells, how deep to bedrock. Didn't need no magic. Just my boo-boo. Gee, thanks, you guys. Sure wish my old boss knew about this. He was not so forgiving at the time.
Hi, all. Sure is my pleasure to know you folks. For my dry hole, here it is. See, where I work, I ain't got no salt. I ain't got no seawater. And sure as hell, I'm begging your pardon, sure as hell I ain't got no glaciers. No siree. What I got is faults. After them easy sections the other guys showed, this is how the Earth is when it gets all broke up. Steep dips and faults. Faults all over. Normal faults, reverse faults, thrust, you name it. Here's my reservoir. Bunch of good sands. 2, 3, 4 of them. Trapped, see, against this fault. It's easy then, says I, after I mapped it. Drill here. Yep, you all guessed it. A dry hole. Good reservoir, but no all. How come? Darn it, I just never paid enough heed to them guys telling me a regular size section don't put dipping reflections where they rightly ought to be. You know, the business where we gets this reflection from way over here, and this bit from way over here, and this from way over here, and this from way over here. But a regular size section plots the reflections slap bang under the shot points, which sure means that dipping reflections ain't where they ought to be. So we got to go to the processors, and they migrate the section, move the reflection a piece that way, from the regular section to the migrated section, from the regular section to the migrated section. So there it was. I done drilled the hole here, where it should have been here about a mile away. Got it okay second time, come in powerful good. But them dry holes, they sure don't let a guy get feisty. You got any dips, you sure better figure out where them reflections are coming from. Mighty grateful to y'all, partner.
Well, there it is. What do we learn? We learn that the seismic method allows us to see down into the Earth. We can see deep in the Earth the major layers, their dips, their faults, their structures, their traps. We are the eyes and the ears of the petroleum geologist. Together, we are the oil finders. We learn that this is done by making a big bang and by timing the echoes. We record the vibrations of the surface of the ground in response to the bang, and we manipulate the results into the form of a seismic section. We learn that to a first approximation, the seismic section may be viewed as a geologic section. And this, of course, is the great strength of the seismic method, that the seismic section has a direct and immediate message as a geologic section. But we learn also that the seismic section is not a geologic section, only a first approximation. And if we take it too literally as a geologic section, then we shall drill more dry holes than we should. So there is our task in this series. First, to learn how to practice the seismic method in the field and in the processing center. And second, to learn how to interpret the results. How to know when the simple message of the seismic section is correct, and how to know when it must be treated with caution. To do this, the career geophysicists among us must now get down to the nitty-gritty. We're going to study some signal theory and some rock physics and lots of practical technology. But before we do that, let me just have a word with our other friends. You see, in this videotape series, we are trying to serve several needs. Perhaps, for example, you are a production engineer or a financial man concerned with the risk element in the exploration business. Or perhaps you are a lawyer or a geological technician seeking to broaden your general knowledge of the exploration game. We hope we've done that for you in these first two tapes, that we've told you something of the game itself and something of the strengths and the weaknesses of the seismic method. So to you, farewell, thank you, and our best wishes. Or perhaps you are a career geologist. In that case, you need more, but not so much more that you get bogged down. Let me suggest just 3 more tapes. 301, Introduction to Fieldwork, 401, Basic Processing, and 501, Introduction to Interpretation. They're still fairly light-hearted. I'll see you in 301 then. And that leaves me with my brethren, the career geophysicists. We hope we won't lose all lightheartedness, but we do have to get on with that nitty-gritty. Remember, please, to read the manuals for each tape before pressing on, and to test your understanding with the questions that you'll find there. That done, on we go. See you in 201.
This program has been sponsored in part by the following companies: Agip, Aramco, City Service, Dome Petroleum Limited, Gulf Oil Corporation, Mobil Oil Corporation, Phillips Petroleum Company, Standard Oil of California, Texaco Incorporated, IHRDC and these companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein. The user hereby agrees to hold IHRDC and the sponsors jointly and severally harmless from any and all damages, including legal expenses, which may arise from the use of this program. No portion of this videotape may be reproduced without the permission of IHRDC.